Swayam Prabha. Digital India. Educated India.
Welcome to this 8th lecture on time series modeling and forecasting. The title of this lecture is Time Series Processes, Introduction and Descriptive Measures. Now, so far we have considered the classical approach of analyzing the time series data. In the classical approach, we decompose the variations in the time series into 4 major components: trend, seasonal, cyclical and irregular. Now, the problem with this classical approach is that it does not provide you any idea of how the current observation is affected by the past observations or past shocks. So, it totally relies on the movement of the time series, the variations of the process. Say trend component, it is a long term movement; seasonal component, it is a periodic movement with period less than 1 year, etc. But how the process is evolving through the past observations, you do not get any idea of how the process is evolving through the past observations or past shocks. So, here are few shortcomings of the traditional method of decomposing time series in various components. It does not provide an insight of link between current observation with the past observations. You do not have any such kind of model in the classical approach which links the current observation with the past observations. Then how the process has evolved due to interaction of past observations and past shocks. You do not get any idea of this phenomenon, how the current observation is interacting with the past observations. Now, in lecture 2, we have considered the regression models. In the regression models, we consider bivariate data, YTXT, say, and then if x and y are highly correlated, x is your input variable or independent variable, y is your output variable or dependent variable. Then if the correlation between input and output variables is high, then you say that your regression line is good, it provides a good fit. Or you can say that the regression is desirable, and the rationale behind it is that highly correlated x y means x has sufficient amount of information about y, and if x has sufficient information about y, then you can use that information for predicting the value of y, and then you use regression technique for predicting the value of y on the basis of given values of x. So, this is the correlation between x and y which plays major role, or the dependence between x and y. Now, in time series, different observations are not independently distributed. So, the correlation might exist between different observations. Now, the question is it possible to utilize, is it possible to exploit this correlation in time series observations to get improved forecasts? So, on one hand, since the observations of the time series are correlated, you cannot apply classical inference procedures. This is a drawback of time series observations. But you can make use of this drawback so that it becomes advantage for you. You can exploit this correlation structure of the time series for providing improved forecasts. But if you want to utilize this kind of correlation structure, you cannot use as such you cannot use the classical procedure for analyzing the time series. So, now I come to the Box-Jenkins approach. This approach became popular after Box and Jenkins published a book on time series in year 1970. The main objective of Box-Jenkins approach is rigorously studying the past observations of a time series. It aims at rigorously studying the past observations of a time series, and then it attempts to develop an appropriate model describing the inherent structure of the series. So, instead of decomposing the variations in the time series into different components like trend, seasonal, cyclical, etc., it attempts to develop an appropriate model for the time series, and actually that model links the current observation with the past observations and past shocks. And if you can successfully develop such kind of model which links the current observation with the past observations and past shocks, then you get the information how the process is evolving through the past observations, and using that model you can also develop proper procedures for making the forecasts. Means you can utilize the model for forecasting purpose. Then the Box-Jenkins approach also attempts to evaluate the properties of the probability model which generated the observed time series. So, what is the probability mechanism which has generated the time series, or what are the properties of that probability mechanism, that probability model which has generated the time series, how is it behaving. So, this Box-Jenkins approach tries to evaluate all these properties also. Now, before coming to the main topic, I first define stochastic process. What is a stochastic process? A stochastic process is a family of random variables yt, where t belongs to say capital T, and capital T denotes the time points at which the process is defined. So, capital T is the set of all time points on which this process yt is defined. So, this stochastic process is not just a single random variable, it is a family of random variables. For a particular t, you get a particular random variable yt, and then for all t, if you consider the set of all yt's for t belonging to capital T, then you get a family of random variables, which is called a stochastic process. Then for the particular t belonging to capital T, suppose S is the set of all possible values of yt, then S is called the state space. For the random variable, such kind of a space is called the sample space. Here it is called the state space. So, yt is a random variable taking values in the state space S, and then this is a common notation. Usually we denote the random variable by y within bracket t if t is continuous, and y subscripted yt if t is discrete. Then this stochastic process yt evolves in time t according to probabilistic laws, and this process provides a probability model for the analysis of time series. So, you get a probability model for the time series. Now, the infinite set of all possible time series is called the ensemble. Remember, for each particular t, you have a state space capital S in which yt can take value, then small t belongs to capital T. So, small t also varies. So, you have an infinite set of all possible time series, and such kind of infinite set is called the ensemble. And if you observe a particular time series or a particular member of the ensemble, then that particular member is a particular realization. So, when you observe a particular time series, the observed time series is a particular realization of infinite set of time series which might have been observed. Then your objective is the evaluation of the statistical properties of the probability model which generated the observed time series. Now, this is something like the regression. What we do in the regression? In the regression also, a relationship between x and y has generated your bivariate data. So, that relation is your probability model. So, your data is generated by a probability model, and since your data is generated by a probability model, it has the characteristics of the probability model from where it has been generated. So, what you do in regression? You try to find out, you try to identify, you try to observe those characteristics of the probability model using your bivariate data. The same thing we attempt here also. Our objective is the evaluation of the statistical properties of the probability model which generated the observed time series. So, it is the probability model which has generated the time series, and since the probability model has generated the time series must be having some information about the characteristics of the probability model from where it has been generated. So, on the basis of observed time series, you try to study, to evaluate the statistical properties of the probability model which has generated it. Again we define some descriptive measures which are quite useful in studying the properties of the time series. Now, for describing the marginal behavior of y t at a particular time point, we define mean function, say mu t, which is simply the expected value of y t. So, expectation of y t is equal to mu t, and this mu t is called the mean function. Similarly, variance function sigma square t is equal to expectation of y t minus mu t square. And then the measure of extent of dependence between y t and y t plus k is, now we define some measures of dependence between y t and y t plus k. So, the first measure is auto covariance function. We also write it as ACVF, auto covariance function, and we denote it by gamma k t. It is the covariance between y t and y t plus k. Again, covariance is defined as expectation of y t minus mu t into y t plus k minus mu t plus k. Obviously, if you take k equal to 0, then what you get? For k equal to 0, you get expectation of y t minus mu t square, which is the variance of y t or sigma square t. So, if you take k equal to 0, gamma 0 t is equal to sigma square t. Now, we define autocorrelation function of lag k. Rho k t is equal to gamma k t divided by sigma square y t sigma square y t plus k to the power half. Means how we define correlation coefficient between two variables x and y, the covariance between x and y divided by square root of variance of x into variance of y. So, same formula we have used here also. Again, for k equal to 0, since gamma 0 t is equal to sigma square y t. So, for k equal to 0, rho 0 t is equal to 1. Now, suppose we assume that mu t and sigma square t do not depend upon t. So, mu t is equal to mu. We also assume that gamma k t is equal to gamma k. So, the auto covariance function depends only on the lag k. Actually, this k is called the lag because say gamma k t. What is gamma k t? It is the covariance between y t and y t plus k. So, y t plus k is the value of y at time point t plus k, and y t is the value at time point t. What is the difference between these two? It is k. Or you can say that y t is lagging behind y t plus k by k terms. So, gamma k t depends just only on the lag k, it is independent of t. Then autocorrelation function rho k is equal to gamma k upon gamma 0. Then ACF satisfies the following properties. So far we have not defined the stationary process. I will define the stationary process later on, but we assume that the process is stationary. Then rho k is equal to rho minus k. Mod of rho k is less than or equal to 1. Now, this is quite obvious because correlation coefficient always has mod value less than or equal to 1. So, you can easily verify it. Further, what is rho k? It is the correlation coefficient between y t and y t plus k. This is your gamma k, rho k. And rho minus k is equal to, this is the correlation coefficient between y t and y t minus k. Here you have lag k, here you have lag minus k, but this is also equal to the correlation between y t minus k and y t. Now, the lag is k, t minus k is equal to k, and since we have assumed that rho k does not depend upon t. So, this is also equal to rho k. Non-uniqueness. A stationary normal process is completely determined by its mean, variance and autocorrelation function. You know that the multivariate normal distribution, it is completely determined by its mean vector mu and the variance covariance matrix sigma. So, if you know the value of mu, if you know the value of capital sigma, then you can uniquely define the multivariate normal distribution or the PDF of multivariate normal distribution. Similarly, here also, if the mean of the process is fixed, if the variance of the process is fixed, and if the ACF autocorrelation function of the process is fixed and known, then these three quantities completely determine the process, a stationary normal process. But it is always possible to obtain several non-normal processes with the same ACF. So, if you do not impose the condition of normality, if you relax the condition of normality, then you may find more than one processes having the same ACF. Now, suppose we consider the ACF of purely random process or Gaussian, this is also called Gaussian white noise process. Why is it called white noise process? This point I will discuss in some other lecture, when I will teach you the frequency domain analysis. But rho k is equal to, now purely random process means it is just like the irregular component of the time series, means UTs are identically independently distributed, and since UTs are independently distributed, they are uncorrelated. So, rho k is equal to 1 if k is equal to 0 and 0 for k not equal to 0. Anyway, we will discuss the purely random process later on in detail. Now, suppose y t is a time series having expectation of y t equal to mu, then autocorrelation function of y t, that is rho k, is the value of A which minimizes expectation of y t minus mu minus A y t minus k minus mu whole square. We prove this result. So, you have to minimize this quantity with respect to A. We differentiate it with respect to A, and differentiating it with respect to A gives you 2 times expectation of y t minus mu minus A y t minus k minus mu into y t minus k minus mu, and you get minus sign here, and then you put it equal to 0. This implies that, just take this minus 2 towards the right hand side, the expectation of y t minus mu into y t minus k minus mu is equal to gamma k minus A times expectation of y t minus k minus mu. You get expectation of y t minus k minus mu square here, which is gamma 0 equal to 0, and then this implies that A is equal to gamma k upon gamma 0, which is rho k. So, we get the required result that the ACF rho k is the value of A which minimizes this quantity. Now, we define the sample autocorrelation function and sample autocovariance function of lag k. Now, suppose you have n observations y1, y2, yn, this is the observed time series. Then first we form n minus 1 pairs. Say you form the pairs y1, y2, y2, y3, so on yn minus 1, yn. So, you form n minus 1 pairs. Then the sample auto correlation coefficient, or it is also called the serial autocorrelation coefficient of lag 1 is defined as R1 equal to now actually you have pairs of observations. So, it is just like defining the correlation coefficient for this pair of observations. So, instead of x1, x2, xn, you have y1, y2, yn minus 1. In place of y1, y2, yn, you have y2, y3, yn. So, you simply use the formula for correlation coefficient. You get this formula R1 equal to this quantity. Here y1 bar is the mean of first n minus 1 observations, and y2 bar is the mean of observations from t equal to 2 to n. Now, suppose y bar is the mean of all the n observations, y bar equal to 1 upon n summation t equal to 1 to n yt. Now, what is the difference between y1 bar, y2 bar and y bar? In fact, in the series which has defined y1 bar, you have n minus 1 terms starting from y1 to yn minus 1. The series which has on the basis of which you have defined y2 bar has terms from y2 to yn, and the series on the basis of which you have defined y bar has terms y1 to yn. So, there is not much difference between the means, and at least when n is large, you will not find much difference between y1 bar, y2 bar and y bar. So, at least for large n, if n is large, then you can approximately say that y1 bar is equal to y2 bar is approximately equal to y bar. Similarly, for the sample variances also, you can write 1 upon n minus 1 summation t equal to 1 to n minus 1 yt minus y1 bar square approximately equal to 1 upon n minus 1 summation t equal to 2 to n yt minus y2 bar square, and this is approximately equal to 1 upon n summation t equal to 1 to n yt minus y bar square. This is the variance for all the n observations of the time series. This is the variance for first n minus 1 from starting from t equal to 1 to n, and this is the variance of observations starting from t equal to 2 to n. So, approximately all these variances are equal, and at least for large n. So, usually we approximate R1 by this formula. Again, for large n, n upon n minus 1 is also approximately equal to 1. Or the n minus 1 is approximately equal to n. So, you can write R1 approximately equal to summation t equal to 1 to n minus 1 yt minus y bar yt plus 1 minus y bar divided by summation t equal to 1 to n yt minus y bar square. Now, this is the sample auto correlation coefficient of lag 1, right. This is ACF of lag 1. Similarly, you may define the sample autocorrelation function of lag k, ACF of lag k. So, you have n minus k pairs, the lag between yk plus 1 and y1 is k, lag between yk this yk plus 2 and y2 is k, and so on. Then we define ck. This is the sample ACVF, autocorrelation function, equal to 1 upon n minus k, summation t equal to 1 to n minus k, yt minus y bar, yt plus k minus y bar, which is approximately equal to 1 by n, summation t equal to 1 to n minus k, yt minus y bar, yt plus k minus y bar. So, approximately for large n, n minus k is written as n. So, sample autocorrelation function of lag k, R k is defined as summation t equal to 1 to n minus k, yt minus y bar, yt plus k minus y bar divided by summation t equal to 1 to n, yt minus y bar square. Now, suppose you divide both the numerator and denominator by n, then what you get in the numerator? This numerator is Ck and denominator is C0. So, Rk is equal to Ck upon C0. Now, correlogram is the graph of Rk against k. The graph of Rk against k is called the correlogram. Now, this autocorrelation function actually plays very important role in identifying a proper model for your time series. So, we use it for model identification. Another tool which is very frequently used for model identification purpose is the partial autocorrelation function. The partial autocorrelation function of order k, say alpha k, is the partial correlation coefficient between yt and yt minus k, conditional on the intermediate values of the process. So, here also we have defined the partial autocorrelation function as we defined for this set of random variables. Say suppose you have 3 random variables x, y and z. How do you define the partial correlation coefficient between x and y? So, we define the partial correlation coefficient between x and y as the correlation coefficient between x and y after eliminating the effect of z. And how do we calculate it? We run the regression between x and z, obtain the residual. We run the regression between y and z, obtain the residual, and then we obtain the correlation coefficient between these two residuals. This gives you the partial correlation coefficient between x and y given z. The same procedure we are going to apply here also. So, suppose alpha k is the autocorrelation between yt and yt minus k. After removing the linear dependence of yt and y t minus k on the intermediate values means y t minus 1, y t minus 2, so on y t minus k plus 1. And then E t k minus 1 is the least squares residual of linear regression of y t and y t minus 1, so on y t minus k plus 1. So, we run the regression between y t and these intermediate values, and then we obtain the least squares residual, which is E t k minus 1. We denote it by E t k minus 1. Similarly, E star t k minus 1 is the least squares residual of linear regression between y t minus k and these intermediate values. Then the partial autocorrelation function PACF alpha k is the correlation between E t minus k and E star t k minus 1. So, the definition of partial autocorrelation function is very similar to the partial correlation coefficient. We have actually adopted similar kind of approach. Now, we derive the expression for the partial autocorrelation function. So, for deriving the expression for the partial autocorrelation function, naturally you have to obtain these two residuals E t k minus 1, this one, and E star t k minus 1. You obtain these two residuals and then you find out the correlation coefficient between these two residuals. Without loss of generality, we assume that sigma square y is equal to 1. So, variance is 1. So, that you do not have to divide by the variance each and every time. So, again the process has variance which does not depend upon t. We assume that the variance does not depend upon t. Then we are going to use some matrix notations. We write z k minus 1 equal to y t minus 1, so on y t minus k plus 1 transpose. Then we have expectation of y t z k minus 1 equal to, we write the value of z k minus 1. So, we have assumed that the mean is 0 and variance is 1. So, expectation of y t minus 1 is rho 1, expectation of y t minus 2 is rho 2, and so on. Expectation of y t minus k plus 1 is rho k minus 1, and then we take transpose of this. And we write it equal to say rho k minus 1, this factor. Similarly, expectation of y t minus k z k minus 1 is equal to, you take this expectation, again expectation of y t minus k y t minus 1 is equal to rho k minus 1. Expectation of y t minus k y t minus 2 is equal to rho k minus 2, and so on, and the last term is rho 1, and then you have transpose of this. So, we write it equal to rho star k minus 1. Say. You observe that the ijth element of p k minus 1 is rho mod I minus j. For instance, if you take I equal to k minus 1 and j equal to 1, then this is equal to rho k minus 2, this element is for I equal to k minus 1 and j equal to 1. Now, suppose R mod I minus j denotes the ijth element of the inverse of this matrix, p k minus 1 inverse. Now, we can write rho star k minus 1 transpose p k minus 1 inverse rho star k minus 1 in this summation form, summation I equal to 1 to k minus 1, j equal to 1 to k minus 1, r mod I minus j, rho k minus I, rho k minus j. And then we take I transpose I dash equal to k minus I, j dash equal to k minus j. So, you can write this summation in this form, and then ultimately this is equal to rho k minus 1 transpose p k minus 1 inverse rho k minus 1. So, this shows that these two quantities are equal. Now, suppose E t k minus 1 is the least squares residual of linear regression between y t and z k minus 1. So, for obtaining E t k minus 1, you have to minimize eta 1, just like the method of least squares, and then you can write eta 1 as 1 plus alpha transpose p k minus 1 alpha minus twice alpha transpose rho k minus 1. We differentiate eta 1 with respect to alpha and put it equal to 0, and this leads to alpha equal to p k minus 1 inverse rho k minus 1. So, we can substitute the value of alpha in the expression for E t k minus 1, this expression, and finally, we get E t k minus 1 equal to y t minus rho k minus 1 transpose p k minus 1 inverse z k minus 1. Similarly, you can obtain the least squares residual of linear regression of y t minus k on z k minus 1, and we denote the residual by star t k minus 1, and the final expression for E star t k minus 1 is y t minus k minus rho star k minus 1 transpose p k minus 1 inverse z k minus 1. So, these are the expressions for two residuals, and your objective is to find the correlation coefficient between these two residuals. Then first we obtain the variances of these residuals. Variance of E t k minus 1 is equal to square expectation of square of this quantity. Now, if you take a square of this quantity and then you take expectation, then the first term is y t square, expectation of which is 1, and similarly you can find the expectation of other terms, and the final expression is 1 minus rho k minus 1 transpose p k minus 1 inverse rho k minus 1, and you can easily verify that the variance of E star t k minus 1 is also the same. So, the variances of these two residuals are equal, and this is the expression for their variances. Now, you have to obtain the covariance between E t k minus 1 and E star t k minus 1. The covariance is given by expectation of product of these two terms. So, we take product of these two terms. So, y expectation of y t and y t k minus 1 gives you rho k. Similarly, expectation of minus rho k minus 1 transpose p k minus 1 inverse z k minus 1 into y t k minus 1. So, you can easily verify that expectation of z k minus 1 into y t minus k is equal to rho star k minus 1. Similarly, you can find the other expectations, and finally, you get this expression for the covariance between these two terms, these two residuals. This is the final expression for the partial autocorrelation function of order k. Simply you have to take this covariance in the numerator and this variance in the denominator. So, this expression gives you the final expression for the partial autocorrelation function. Just take note, stop करिए. So, in this lecture we have defined various moments of the time series process, like mean of the process, variance of the process, autocorrelation function, autocovariance function, and then we have also derived the formula for the partial autocorrelation function. And we have also defined the corresponding sample quantities, sample mean, sample variance, as well as sample autocorrelation function and sample autocovariance function. These partial autocorrelation function and autocorrelation function play a very important role in identifying a process, particularly their sample estimates. If you take the sample estimate of autocorrelation function, say suppose R k is the estimate of rho k, and you plot R k against k, then this plot is called the correlogram, and using this correlogram you can identify or you can distinguish between different time series processes. Similarly, if you consider the sample estimate of partial autocorrelation function, which you can easily obtain by replacing the parameters by sample estimates in the expression for partial autocorrelation function. Then you can also plot the partial autocorrelation function against k, and this graph of partial autocorrelation function, sample partial autocorrelation function also helps you in identifying different time series processes. So, this is how sample autocorrelation function and sample partial autocorrelation function can be used for the model identification purpose. Now, in the next lecture I will consider the stationarity of the process. We will define the stationarity of the process and why stationarity is required for studying the properties of a time series model. So, we will come to this topic in the next lecture. Thank you.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said, but also in what remains unsaid. Today I will be reading one of the shortest instances of a short story that I have ever encountered, and indeed the very charm of this particular story that I am going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I'll be reading out is perhaps the closest to the one that Maugham wrote. The story is titled, in all of its adaptations almost, as Appointment in Samara. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. Can you please lend me your horse so that I can fly away from Baghdad to the town of Samara and thereby escape death? The master, being a good man, gave his servant his best horse and saw him gallop off to Samara to escape death. Then the master himself went to the marketplace and confronted death. Why did you make a threatening gesture to my servant? Asked the master to death. And death replied, it was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samara. See you in the next episode of Literary Snippet.